So our question number 1 says, which of the following color of white light deviates most when passes through a prism? So maximum deviation will be for violet. Okay. So violet will be deviated the most and the least is the red one. Clear? So this is our first answer. Let's move to question number 2. For a total internal reflection, which of the following is correct? Light travels from rarer to denser? No. Light travels from denser to rarer medium? Yes. Light travels in air? No, it travels in everywhere. Okay. So correct answer is option B. Light travels from denser to rarer medium. So when it goes from denser to rarer medium, it bends away from the normal, and as we go beyond critical angle, total internal reflection takes place. So hence correct answer is B. Let's move to question number 3. One metallic sphere A. So let's draw a sphere. Let's say this is our sphere A. Is given a positive charge. Okay. Whereas another identical metallic sphere B, this is our B, okay, it is given exactly, B is of exactly same mass as of A, and it is given equal amount of negative charge. Okay, fine. Then masses, they are talking about masses. So if something is given positive charge means electrons are removed, and if electrons are removed, the mass will decrease. So here the mass is decreased for A. While if you are giving a negative charge, a lot of negative charge, you are adding electrons, yeah, because electrons are negatively charged. So if you are adding electrons, it is getting a negative charge. Hence, the mass will increase. So mass of B will increase. So let's now read the question. Mass of A and B will still remain equal? No. Mass of A is increased? No. Mass of B is decreased? No. Mass of B increases? Yes. Because of the extra electrons, mass of B will be increased. Correct? Let's move to question number 4. The relaxation time in conductor decreases with the increase of temperature. Okay, that's a direct relation. So temperature, increase in temperature, our relaxation time decreases. So correct answer is option B for question number 4. Let's move to question number 5. It says a cell of internal resistance R connected to an external resistance R. The current will be maximum only if R is equals to R. So this is an important condition, that when R becomes equal to R, okay, the equivalent resistance become minimum and maximum current will pass through the circuit. Okay. Let's move to question number 6. It says a figure shows 3-point charges plus 2q, minus q and 3q here. Okay. Two charges 2q and minus q are enclosed within the surface S. What is the flux due to this configuration through the surface S if the value of q is this? Okay. So we should know that if the closed surface here, our Gaussian surface is this one. Okay. Our closed surface is this one. So if this is our closed surface, what will be the flux? According to Gauss's law, the flux phi will be equals to the total charge enclosed. So Q in is charge enclosed upon epsilon naught, right? So what is the Q in? Q in is 2q plus minus q whole divided by epsilon naught. And what is 2q minus q? It will be q upon epsilon naught. And what is the q value? As per the question, it is 885 millicoulombs. Small m means milli. So this will be 885 into 10 to the power minus 3 upon epsilon naught. 8.854 into 10 to the power minus 12. Okay. When you remove this point, okay, since they have taken 885, let's ignore this 4. So when you remove this, you will get into 100. Okay. Let's cancel this with this. So you left with 10 to the power minus 1 whole into 10 to the power plus 12. So this will be 10 to the power 11. And what's the unit of flux? Flux unit is our charge, which is coulombs, and epsilon, or you can put directly flux phi is E into area, so which is Newton meter square per coulomb. That's our unit for flux phi. This was question number 6. Let's move to 7th one. An object is placed at a certain distance from a convex lens of focal length 20 centimeter. So convex lens means focal length will be positive. So f is 20 centimeter, right? Find the distance of the object if the image is magnified 4 times. So image is magnified 4 times, magnification is 4. Now they are not talking about real, virtual, okay, or anything like that. So we will take two situations here. Magnification will be plus 4 if it is virtual. So let me write here in bracket virtual, okay. We will solve it for virtual separately, and magnification will be minus 4 if it is real, right? Great. Now, what's our lens here? So what's our magnification formula? 4 will be equals to plus V by U, okay? So this means our V will be equals to 4 times U, correct? And if V is 4 times U, let's use our lens formula. 1 by V minus 1 by U equals 1 by F, correct? let's substitute here. V is 1 by 4u minus 1 by u, and f is how much? 1 by 20, correct? Now let's take 1 by u common out. So in bracket you left with 1 by 4 minus 1, and that is equals to 1 by 20. So this will be 1 by u, and 1 by 4 minus 1 minus 3 by 4, right? When you solve it, you will get minus 3 by 4 equal to 1 by 20. And when you take u on the other side, it will be minus 3 by 4 into 20 is equals to u. So 4 5s are minus 15. That minus 15, that will be your u. Okay. If everything in centimeter, then minus 15 will be also in centimeter. So minus 15, which means object distance is less than focal length. Hence, the final image formed will be virtual, right? This was the condition. Now, let's say if the image, because the question is not speaking clearly about real or virtual. So let's solve for real also. So if the final image is formed at real, then magnification is minus 4, and we can write here V by U equals minus 4, correct? And V will be equals to this time minus 4U. Again, making use of our lens formula, 1 by V minus 1 by U equals 1 by F, correct? Now let's substitute here minus 1 by 4U and minus 1 by U, and that is equals to 1 by 20, correct? Now next is take 1 by U common out. You left with minus 1 by 4 minus 1 equals to 1 by 20. Next is let's cross multiply and simplify. You will get here 4 and 1 minus 5 by 4. Okay, that's equal to 1 by 20. Let's take this u on the other side and 20 on this side. So minus 5 by 4 into 20 equals to u. Okay, so 4 5s are and 25 minus 25 centimeter. As you can see that object distance this time is greater than the focal length. Hence the image formed will be real. So these are the two possible situations for question number 7. Let's move to question number 8. Oh, there is an OR part also for question 7. Under what condition does the phenomena of total internal reflection takes place? Okay, so the condition here is, first condition, the ray of light must travel from a denser medium to the rarer medium. Okay, this is our first condition. Second condition is the angle of incidence must be greater than critical angle for that medium. So this is our, okay, two conditions. Now question second part says draw a ray diagram showing how a ray of light deviates from 90 degree by 90 degree after passing through a right angled isosceles prism. Okay, so let's draw an isosceles prism here. So let me draw here a prism, isosceles prism. So let's make it like this. This is right angled isosceles prism. Sir, what is isosceles triangle? A triangle, okay, in which the two opposite sides are equal. Okay, so if it is 90 degree over here, then this is obvious that perpendicular and base must be equal, right? So this angle will be 45 degree here, and this will be also 45 degree, correct? Why they are 45? Because it's isosceles, right? And if let's say if the rays are going, okay, so this is a ray which is going like this and hitting here, okay, at this point, and let's draw a normal to this point. So let's say this is our normal to this point. What is normal? Perpendicular. Perpendicular to whom? This hypotenuse, right? You can see that it's making 90 degree over here. Then if this is 45 degree, this will be how much? This will be 45 degree, correct? Okay. Or you can say if this line is parallel to the base, then this angle and this angle will be corresponding angle, right? And if it is corresponding angle 45, 45, then this angle will be 45, right? So if it is 45, angle of incidence is 45, what will be the angle of reflection? Okay, at this face, angle of reflection will also be 45. It will be straight line downward, correct? So this is our incident ray and this is our reflected ray. Okay, I hope this is clear. Okay. Now why it is reflected back to the medium? Okay. Because we know here that our critical angle, okay, this angle here is critical. It is forming a total internal reflection. So similarly, if you draw another ray here, this will go parallel and it will pass here. Okay. Clear it is? So this will be a very important ray diagram for right angle isosceles triangle. So A, this is B, and similarly you will get here A dash and here it is B dash. Okay. So this was the ray diagram. Only ray diagram is asked. Yes. Let's move to question number 8. A potential difference V is applied across a conductor of length L. So let's imagine this is our conductor and potential difference is V is applied across it and length of the conductor here is L. How is the drift velocity affected when V is doubled and L is halved? So first of all, what is our drift velocity? Our drift velocity Vd is equals to minus E tau by mass of electron, Me, right? And if I take the magnitude means ignoring the negative sign, it will be E tau by Me. Let's talk a little about other variables here. So let me write here, E is the charge of the electron. Charge of electron. Capital E is electric field, the external electric field which we are applying to the given conductor. Tau is relaxation time. And Me, mass of electron. Now the question is saying what is increased? Now our potential, okay, is doubled, V is doubled and L is halved. When you double the potential and change the length, okay, who will be affected out of these 4 variables here? Okay, electric field. How? We know that electric field E dot L is equals to V. Electric field into length of the conductor is potential. So E will be equals to V by L. Let's substitute here in our drift velocity. So Vd will be equals to E tau by Me, and in place of capital E, this electric field here, I am putting V by L. Correct? This will be our formula. Now they are saying V is doubled. So if V is doubled and L is halved, then what will happen? V dash will become V into 2 and L dash will be L by 2. So what will be the new drift velocity? Vd dash, that will be the new drift velocity. Other parameters are constant, okay, and V changes to V dash upon L changes to L dash. Let's substitute the values. On substituting, what we will get? We will get E tau by Me, correct? V dash twice of V upon L dash, L by 2. This 2 will go up and we get our final expression as, okay, I am writing here. So from here to this is here I am writing Vd dash will be equals to 4 times E tau by Me into V by L. Now this E tau V by L, Me is nothing but our previous drift velocity. So new drift velocity is 4 times the previous drift velocity. Correct? So this is our result for this particular problem. Let's see the 9th one. In which orientation a dipole placed in a uniform electric field is in stable configuration? Stable means it's not experiencing any torque. Okay. So if for the first case, if theta is 0 degree, okay, this implies sine theta is 0. Hence, the torque, okay, is 0. Because torque tau is Pe sine theta. And if torque is 0, this configuration, this is A. This configuration is a stable equilibrium. Second part says unstable. So unstable is counter torque. You can say if theta is 180 degree, correct? In that case, again sign will be 0, but it will be in opposite direction. So if theta is 180 degree, okay, the dipole will be in unstable equilibrium. Okay, so this is our answer, because here in this case the dipole is aligned anti-parallel to the electric field. Okay, so this is our unstable equilibrium. Let's move to question number 10. Explain the mechanism of the flow of current in a metallic conductor, hence derive a relation for drift velocity and relaxation time. So let's explain it. Initially, so let me write it in words. Initially, when there is no external field, when there is no external electric field, the electrons in a conductor, metallic conductor, are oriented in random directions. Okay. So you can imagine this situation like this. So this is our metallic conductor and electrons are random. Some are going in this direction, some are in this direction, some are in this, all are in random directions. Okay. When we apply an external electric field, these electrons experiences a drag force which results in a drift velocity. Okay, so what is this drag force? Okay, so we know that this drag force is given by F equals to QE, correct? From which chapter? First chapter, Coulomb's law. Charge into electric field, where E is the external field. And how does the conductor now looks like? Now the conductor will have, in presence of external field, all these electrons are aligned in the direction of the external field, correct? So this is in presence of field and that is in absence of external field. Be very careful, we are talking about external field because internal field is 0 for a conductor, right? So here now, due to an external field, they experience a force which is given by this. From 11th standard, we know that force is nothing but mass times acceleration, that is Newton's second law, correct? And if we go specific here, this charge on here is charge on an electron, so it is minus EE, correct? So acceleration produced will be equals to minus EE by M. Be very careful, this M is mass of electron, so let me write here ME, equation 1. Now let's write here from equations of motion, 11th standard, we know that final velocity of any particle V will be equals to U plus AT. This is the first equation of motion in 11th standard, right? We also learned it in 9th standard. So V is the final velocity, U is the initial velocity, A is the acceleration, T is the time. Now here, since we are talking about so many electrons at a time, we will go for average. So average final velocity will be equals to average initial velocity plus acceleration into average time. Correct it is? Okay. So this is very important because A is a factor which depends on EE by ME, where E and ME are constant. So electric field is also constant. So A is not averaged, right? Be very careful. Why we have not placed here sigma? Because E is constant, 1.6 into 10 raised to minus 19, ME 9.1 into 10 raised to minus 31, and capital E is electric field. So all of them are constant when you are taking a particular case, right? So this. Here average V will be nothing but drift velocity produced in the electrons. We write it as Vd. D is the suffix here. Average initial velocity. So let me write here sigma U is equals to 0 because they are all randomly oriented. U is a vector quantity. So all the vectors will give you resultant 0. And sigma, the average time here, is a very important parameter which we call it as relaxation time. So tau is a relaxation time. So here A, sigma U is 0. A is minus EE by ME and sigma T is tau. So drift velocity our will be Vd, which is equals to minus EE tau by mass of electron. This is our drift velocity. Let's read the question if they are asking anything else. So explain the mechanism of flow of current in a metallic conductor. So current will flow only if external field is applied. Okay. Hence derive a relation between drift velocity and relaxation time. So this is a relation between drift velocity and relaxation time, right? Let's move to question number 11. 11th one says, consider the given figure, okay, and find the equivalent capacitance between A and B. Let's first solve the A part. So equivalent capacitance between A and B. So we can see here, if you start from this point, okay, between these 2 points, this 2 and this 3, they are in series or parallel? They are in parallel. So what is the equivalent of parallel? Equivalent of parallel will be C equivalent, okay, will be equals to in parallel C1 plus C2. Be very careful. Don't do the mistake of resistor. In resistors, it's 1 by. Here it is straight away. So 2 plus 3, it will become 5 microfarad. Okay. So let's redraw our diagram so that we become clear with this concept. So here we have a battery. I'm not writing the voltage initially because we are finding the equivalent here. So this is our 10. And here we have 5 just now we found. And finally we have here a 12 microfarad and this is connected here. And this is A dash. If you are confused, this is B dash. So between A dash, B dash, we got 5 and this is 12. Now all of them are in series. So what is our formula for series? So C equivalent, okay, I'll call it as C dash here, okay. Now let's call it as C equivalent of this whole circuit. That will be 1 by 12 plus 1 by 10 and plus 1 by 5, okay. Now 12 5 is 60 and all of them have common parameters. So 60 here, and be very careful. This is 1 by C equivalent. Some students write, okay, C equivalent and things get wrong because at the end you have to reciprocate it, right? So 12 5 is 60. 10 6 and 5 12. Okay, so this will give us 12 and 6 18, 18 and 5 it will be 23 by 60, 1 by C equivalent. Okay. And this implies the whole equivalent of this whole is 60 by 23. This is our equivalent capacitance of this whole circuit, right? 60 upon 23. Let me just go through it once again. So 2 and 3 are in parallel. So they give us 5 microfarad, and when you find 10 and 12 and this, so this becomes 12 5 is 60, 10 6 and 5 12, right? So 12 and 5, 17 and 17, okay, and 6 is 23. Yeah, correct. So this is 60 by 23 and of course that is in microfarads. So be very careful. This is in microfarads. Okay. This is our equivalent capacitance. Okay. So that is our part 1. Second part says find the amount of charge on 10 microfarad. Right. So to find the charge, first of all, we have to find what is the total charge which is coming out of the battery. So Q is equals to, so for B part I am writing here, Q is equals to CV. So C equivalent here is 60 by 23 and voltage here is 1000. Okay. And be very careful, microfarad is there in capacitance, so you have to keep it in 10 to the power minus 6. Okay. So this will be 60 by 23, okay, into 10 to the power minus 3. Okay. So minus 3 because 3 and minus 6. So you can further make it as 6 by 23 into 10 to the power, or you can keep it as 60 by 23 millicoulomb, right? Millicoulomb. Okay. So that is the charge. Now that charge is going across the circuit. So if it is going like this, okay, we know that our first capacitor, okay, this will be the charge will not change there because remaining part are in, so they are all in series this, okay. So here it will be 60 by 23 millicoulomb. That's our final result. Let's move to OR part of this question. The OR part says the electric potential V at any point in space is given by, so V here is given by 20x cube plus 3y square plus 2z square. Okay, this is our potential, where x is in meters. Okay, calculate the electric field intensity. Okay, at point is given, P is 1, 0, 2. So basically x and z values are given. So what you have to do, we know if it is a function of x, y and z, we know that our it should be gradient, right? So how do we find electric field E is equals to minus dV by dr. Okay, be very careful, where r can be x, y, z, it can be in terms of that. Here we are given with a value or in terms of, it's a multivariable function. We are given in terms of x, y and z. So what we will do, we will differentiate it with respect to x first. So d by dx, okay, of this whole thing. So when you are differentiating it with respect to x, okay, you will keep y and z as constant. You will assume them as a constant, okay, minus d by dy, okay, of this whole thing, 20x cube plus 3y square, okay, plus 2z square, okay. This will be, and finally let me just take it on this little on the other side, so that we will have more space. Okay, so this, okay, and finally a minus d by dz of this whole function. So let me just write it, 20x cube plus 3y square plus 2z square, right? Okay, now since this is along x-axis, okay, so electric field is a vector quantity, be very careful, and this is a scalar quantity. Here it will have I cap, okay, this will have j cap, and that will have k cap. Okay, so let me differentiate it. So derivative of this will be minus 60x square, right? Differentiation, if you know, so derivative of x cube is 3x square, so 3 2s are 6 x square. What about other y and z? 0, so it's minus 60, and minus when you differentiate y, so it will become 6y j cap, other one will be 0. When you're differentiating z, it will be, how much our z is 2z square, so 2 2s are 4, so it will be plus 4z k cap. Okay, this is our electric field vector quantity. Now if this is our electric field, okay, what will be electric field at point 102? So let's put x as 1, so putting here minus 60i, 0 and 2 plus 8k. So this is our answer for question number, which one it was, or part of 11th one. Okay, so question number 11, this is our answer for. Let's move to 12th one. Charges of 5 microcoulomb, 10 microcoulomb and minus 10 are placed at the corners, okay, in air at the corners ABC of an equilateral triangle. So let's imagine now that this is our equilateral triangle, okay, and in this equilateral triangle, let's put here charges. This is our 5 microcoulomb, this is our 10 microcoulomb, and this is minus 10 microcoulomb, right? Okay, this is equilateral of 5 centimeter. Each side is 5 centimeter. Determine the force on A. So let's put it here as A, B, C. Okay. Now pay attention. Since force is a vector quantity and we are dealing with Coulomb's force. Okay. So first of all, force on A due to be attractive or repulsive. Okay, it will be repulsive. Why? Both are positively charged. So it will be repulsive in this particular direction. So this is force on A due to B. Now force on A due to C, it will be attractive or repulsive? Of course it will be attractive, because one is positive and another one is negative. So it will be in this direction, right? So this is force on A due to C. Now what will be the angle? This angle. We know this is an equilateral triangle. So this angle is 60 degrees. So outer angle will be 120. So this is 120. And this is very important. First thing, putting the arrows and finding the angles. Once you find the angle, then you can easily find the resultant force. So let's find the magnitude of FAB. So when you are finding force FAB, this will be K, which is 9 into 10 to the power 9. Q1, which is 5 into 10 to the power minus 6. Q2, 10 microcoulombs, 10 to the power minus 6. Whole divided by separation square, which is 5 into 5. And centimeter hai, so this will be 10 to the power minus 4. Correct? Okay, great. So this is our FAB. What about our FAC? FAC is 9 into 10 to the power 9. First charge, 5 into 10 to the power minus 6. Second charge, be very careful. I have not placed here 10 microcoulomb, so 10 is there, yeah. So be very careful with the negative sign. You don't have to take the negative sign. Sir, why? Because we have already included it in the arrows. You made the arrow downward because it was negative. If it was positive, the arrow would be upward, and that will reflect, okay, in the angle also. So be very careful. You have considered the negative sign. So no need of putting it again because it's a vector quantity. What's the separation? 5 into 5 into 10 to the power minus 4. If you look here, FAB and FAC both are equal in magnitude. So what will be their resultant? Let me recall our resultant formula from class 11th. R will be equals to root under A square plus B square plus 2AB cos theta. Theta here is 120, but A and B are equal. If A and B are equal, then this formula will reduce to this format: A square plus 2A square cos theta. And if you take A square common, it will be A square taking common 1 plus 1 plus 2 cos theta. Correct? Okay. So this will be, okay. So this will be, we can further write it and then we can directly put it A square into, this will be 2 plus 2 cos theta. Correct? Okay. Now let's substitute here. So our A, you can substitute anyone, both are same. So A, we can take it out of the root here. Okay. Which A? So this A, we can take it out of the root here. Okay. So if we take it out, then resultant R will be simply A into root under 2 plus 2 cos theta. Now let's substitute here the value. So A is nothing but, so resultant I am writing here. What is the resultant in our case? It will be force on A, right? So we are writing here force on A. Let me write it here. Force on A will be equals to, what is A? A is 9 into 10 to the power 9 into 5 tens are 50 into 10 raised to minus 12 upon 25 into 10 raised to minus 4. Correct? This is our force on A. Root under 2 plus 2 into cos 120. Cos 120 is minus half. Correct? So let's see what we left with here. So this will be 25 and 50. 25 and 50 will cancel out. It will be 2. So 9 into 2 into 10 to the power 9 minus 12 minus 3 into 10 to the power minus 4 goes up plus 4. Root under 2 minus 1. What is 2 minus 1? 1. And root of 1 is 1. So we can ignore the last part. 18 into 10 to the power 1. So 118 newtons. That's the correct answer for this question. This is question number 12. Okay. Let's move to question number 13. State Gauss's law. So let me write here Gauss's law. Okay. Now what is Gauss's law? According to this law, the total electric flux coming out of a closed Gaussian surface is 1 by epsilon naught times the total charge enclosed by it. This is our Gauss's law. Next part says, so basically we have to write the expression also. Flux phi is equals to the total charge enclosed Q inside any closed Gaussian surface by epsilon naught. Okay. Second part of the question says, using Gauss's theorem, derive an expression for electric field due to infinitely long charge wire. So let's imagine this is a wire. Okay. Let's imagine a wire. Okay. So this is our wire. Okay. Let me draw it properly. So let's say this is our, let me make two straight lines here. So first one is this and another one I am making here. So this is our second wire. Okay. This is second part and this is our, wait a minute. This is our complete one wire. Okay. Long cylindrical wire here. Okay. And here we have charges. Let's say plus on this. So electric field due to this positive will be radially outward at each and every point around this along the curved surface area. If you imagine it in 3D, it will be a curved surface area. So let's imagine a Gaussian surface here. So Gaussian surface here will be a cylinder. Okay. And this cylinder has a radii. What is the radii? The length of this, okay, the point at which you are finding the electric field, let's say at this R. And what will be the length of this? L. Okay. So first of all, we know that the flux phi will be equals to how much? This will be equals to our electric field into area. Cos of angle theta, but theta will be 0 degree because the angle between the electric field and normal to the area is 0 degree here. Correct. And which area we are talking about? The upper surface here, this one? No. This one? No. The curved surface area of the cylinder. Okay. And this from Gauss's law, we know from Gauss's law, flux phi is nothing but the total charge. Okay. Q in means the charge enclosed in this whole region upon epsilon naught. That is equals to electric field, which we are looking for, into area. Which area? Curved surface area, 2 pi r into L, the length of the cylinder. This is our equation 1. Now we know that surface charge density, here it is linear charge density because it's along the length. So we know the linear charge density lambda equals to the total charge Q in upon length L, okay, of the wire. So across this L, the total charge enclosed will be lambda into L. Okay. This is our equation number 2. So putting in equation 1, what we will get? We will get, okay, from 1 and 2, what we will get? Lambda into L upon epsilon naught is equals to E into 2 pi RL. L cancels both the sides. We can cancel this L with L. Electric field due to this will be lambda upon 2 pi R epsilon naught. Very important expression. This was our question number 13. Let's see question number 14. Question number 14 says, draw a ray diagram showing the formation of image, okay, in a reflecting type telescope. So let's draw a ray diagram of a reflecting type telescope. So here we have a reflecting type telescope, which is like okay, these are the two lines we will draw here, okay, and we have a mirror over here. We have another mirror over here and we have another mirror over here. This is connected like this, and okay, this is our eyepiece, and here this is our concave mirror. So it is polished from outside like this. Okay, let me recover this properly. And this is over here. Then we have polished this on the other side. Okay, then we have rays which are coming. Okay, so the rays which are coming, this is called secondary mirror. So let me first draw the rays. So this ray is coming like this, it is hitting and it is going in this side, and this is going to converging towards this. Okay. Another ray which is coming here, okay, hitting here, okay, and this is also going like this in this direction. Okay, next is let's see what are the different parts. So here this is called secondary mirror. Secondary mirror. Okay, this is our objective mirror. There are two. And this is our eyepiece. Okay, so this is the ray diagram for reflecting type telescope. Okay, next they are saying write two advantages of reflecting type over refracting type. Okay, so let me write here advantages. First advantage here is these mirrors, okay, because lenses do chromatic aberrations, mirrors don't do. So first one is mirrors doesn't cause chromatic aberrations. Okay, next advantage is, okay, they are easy to build large telescopes. Third one, these are cheaper in cost. So these are the, you can write any two. Okay, let's move to our next question, our question number 15. It says two thin lenses are placed coaxially in contact. Obtain the expression for focal length of combination in terms of focal lengths of the two lenses. Very simple. So basically what we have here is, you have one lens, let's put here, this is one lens over here, and another lens I am putting here. So I am drawing it here. Okay, so let's say these are two lenses. Our first lens here is A and this is lens B. Okay, this is our common principal axis over here, and you are placing any object here O. Okay, and this is, you are getting a final image. Be very careful, this is our final image at I. Okay, so maybe the final image formed, okay, due to the first lens, okay, was little apart. Okay, why it was little away? Because it will be here, this is our I1. Okay, but due to multiple reflections and multiple refractions, this will go and produce a final image here. Okay, because we can see there are different refracting surfaces. There are 4 refracting surfaces here, rarer to denser, denser to rarer, again and again. So image will shift from, instead of I1 to, it will be I1. Okay, the object distance here is U, and the object image distance V1. V1 is the image distance of first one, lens A, and this is our V. The image formed by the first lens always acts as an object for the second lens. Okay, so what we will do here is, we will write for lens A 1 by V1 minus 1 by U equals to 1 by F1. What is F1? Focal length of the first lens. Focal length of the second lens is F2, right? So if for lens A, this is our equation 1. For lens B, the image formed by the first lens acts as an object. So this will be 1 by V minus 1 by V1 equals to 1 by F2. This is our equation 2. Adding equation 1 and 2. Adding equation 1 and 2. 1 by V1 minus 1 by U plus 1 by V minus 1 by V1 equals 1 by F1 plus 1 by F2. And we know that these two will cancel out. Okay, this and this, we left with 1 by V minus 1 by U equals 1 by F1 plus 1 by F2. And what is 1 by V minus 1 by U? That's our 1 by F. So equivalent of these two will be 1 by F1 plus 1 by F2. This is our final outcome. Clear? This was question number 15. Let's move to 16th one. Derive an expression for the potential at a point, equatorial point of a short dipole. Equatorial point. Let me remind you that potential V for a dipole is P cos theta, okay, upon 4 pi epsilon naught R cube, right? And equatorial, at equatorial point, what is angle theta? Theta is 90 degree. Why? Because that's a definition of equatorial point, perpendicular bisector. So perpendicular and bisector to the dipole. So theta being 90 degree, cos 90 is 0. So potential at equatorial point is 0. This is our first one. Two charges minus q and plus q are located at point this and this respectively. Okay. So let's draw a rough diagram here. Our charge here is minus q and plus q. One is at 0, 0 minus a, another is 0, 0 a. Okay. Okay. How much work is done in moving a small test charge from a point this to this along the x-axis? Now, how much work is done in moving a small test charge from the point 500 to -700? Okay. Along the x-axis. Okay, so you are taking along x-axis. These are placed along z-axis. Okay, and let's say this is our x-axis over here, perpendicular to this, and how much charge is taken, how much work is done. So it is from 5 to -7, so 500. Okay, let's draw it here down so that we will get a little more space. So let's take it here. Okay, 500 to, what does our question says, -700. So here it is -700. Okay, so you are taking a test charge. What's the magnitude of charge is not given. So if it is going perpendicular here, so okay, so these are placed here, and how much work is done in moving a small test charge from the point 500 to -700. Now this is perpendicular because this is our z-axis and perpendicular here, right? And this is the origin, so 0 means perpendicular bisector, so potential there is 0. So in this case V is 0. If V is 0, what is U? U is the work done, right? Potential energy, that will be charge into potential. So no matter what is the charge, our work done will be 0. So correct answer here is work done is 0. Let's move to the next part. Does the answer change if the path of the test charge between the same points is not along x-axis? If it is not along x-axis, yeah, it will change. Yes, because it depends. Angle will be different, and in that case, we will find first potential at those points and we will multiply. So yeah, if the path is not along x-axis, it will of course change. So this was 16th one. Let's move to the OR question. Our question says, derive an expression for capacitance of a parallel plate capacitor when dielectric slab is inserted between the two plates. So let's solve the A part. Let's say this is our first one. This is our capacitor. When there was nothing, air in between, the capacitance was C0, which is epsilon naught A by D. Okay. So this is the initial capacitance of the capacitor. A is the area of the plates and D is the separation between the plate. Now you are placing a dielectric slab. Now since it is not specified what is the size of the dielectric slab, so we will take it equal to the size of the parallel plate capacitor. Area also same and separation also same. So if this is the D, this is the dielectric constant with, they have not said what is the K value, so let's assume it as K. What is K? Dielectric constant. So if K is the dielectric constant of this material, what will be the electric field? Electric field in this region will be E0 upon K. Be very careful, this is E0 and that is epsilon naught. Both are different. Epsilon naught, permittivity of free space. E0 is the electric field. Initial electric field. And what is initial electric field? When there was air, it was sigma upon epsilon naught. Sigma by epsilon naught is the electric field, E0. Now due to the introduction of dielectric slab, the electric field becomes E0 by K. So what is the new electric field? So new electric field will be E dash, that is E0 by K. What is E0? Sigma by epsilon naught K. If this is the new electric field, what will be the new potential because of this dielectric? New electric field into the separation, which is same. So this will be sigma upon epsilon naught K into D. And what is sigma from first chapter? Charge upon area. This is the new potential. If this is the new potential, what is the new capacitance? New capacitance will be C dash, which will be Q upon V dash. And that will be Q upon V dash. Q D epsilon naught A K. Q and Q cancelled. What we left with? C dash, which is equals to K times epsilon naught A by D. Correct? And what is epsilon naught A by D? Let's go up. That is C naught. So our new capacitance value will be nothing but K times C naught. This is our first part of this. Let's move to our next part. So our second part says a parallel plate capacitor with air between the plates has a capacitance of 9 picofarad. So let me write here our initial capacitance, our C naught. So C naught here is 9 picofarad. Let's go up and read the question. The separation between the plates is D. So separation between the plates is D. Okay, fine. Next part. It says the space between the plates is now filled with two dielectric. One of the dielectric has dielectric constants K1 and thickness D by 3. Okay, K1 in the thickness D by 3. We will draw a diagram within a minute. And while the other one has dielectric constants K2, which is equal to 6. K2 is equals to 6. Okay, that is 6, and K1 is how much? K1 is 3. Okay, K1 3. And this is 2D by 3. Okay. What will be the capacitance of the capacitor? Okay. Let me read it once again for you. So a parallel plate capacitor is there with air between the plates, has a capacitance value of 9 picofarad, which is the initial capacitance. Okay. And then here we have the separation between its plate is D. The space between the plate is now filled with two dielectrics. One of the dielectric has a dielectric constant 3 and the thickness D by 3. While the other one has dielectric constant 6 and thickness 2D by 3. What will be the capacitance of the capacitor? In case if you have not understood, let's see here. Now, this is quite important. So you have a parallel plate capacitor. Okay. In this parallel plate capacitor, here, when there was nothing, its capacitance value was 9 picofarad, which was epsilon naught A by D. This is when air is there. Now, if this separation is D, 1/3 of the distance, okay, that is filled by first capacitor with dielectric, sorry, and this dielectric is 1/3 here, 1/3 of this, okay, this will be, so what is here? D by 3. And what is dielectric constant here? Dielectric constant here is 3. So electric field will be E by K1, okay, so K1 is 3, K2 is 6, okay, so let's put here K1. Another is 2D by 3, so 2 by D by 3 is here. Okay, so D by 3 1/3 and this is 2/3. Okay, so if you add both, let's see, D by 3 plus 2D by 3, that will give you how much? 3D by 3, which is D. So which means this remaining half, complete space is filled with how much? K2. I hope this is clear. Because if first half is 1 by 1/3, other half is 2/3, right? Correct? And they are placed like this in between. Because of the addition of this dielectric, there will be some change in electric field. So what is the new electric field? New electric field will be E1, that will be E naught, which was previous, okay, upon K1. Okay, and E2, which is the electric field developed, here it is E2 and there it is E1. So E2 will be equals to E naught by K2, correct? I hope this is clear. And E naught is nothing but sigma upon epsilon naught K1. This will be sigma upon epsilon naught K2. I hope this is clear. And sigma is nothing but charge upon area. And this is charge upon area. If these are electric field, can we find the corresponding potentials? Yes. So our first potential will be V1. That will be how much? E1 into the separation D by 3. And V2 will be E2 into what is the separation? 2 by 3D. E1 is Q by epsilon naught A K1 into D by 3. E2 will be Q by epsilon naught A K2 into 2D by 3. Correct? If these are the potentials developed across the two dielectrics, what will be the total potential? The net potential of this capacitance will be V1 plus V2. So when you add both, what are the common terms? Or let me write one more step. So Q by epsilon naught A K1 D by 3 plus Q by epsilon naught A K2 into 2D by 3. Correct? Now let's now take the common terms. So common terms here will be Q, D is common in the both of them. Epsilon naught A and 3 is also common. So what we left with here? 1 by K1, and what we left with here? 2 by K2. Correct? Okay, so in case if you don't know how I took common here, okay, just multiply this with the first term. You will get the first term on the top and multiply it with the second term. You will get back that. This is our potential. If this is our potential, what will be our new capacitance? Our new capacitance will be C dash. That will be equals to, let's call it as V dash, sorry. Q upon V dash. So Q is how much? Q. And V dash, this is given here. So Q and D, to make it simple, okay, let's cross multiply this before we substitute. So let me write here Q D 3 epsilon naught A and in bracket K2 plus 2K1 upon K1 K2. So that when you reciprocate, it becomes easy for you. So Q upon V dash will be Q D into K2 plus twice of K1 and in numerator into 3 times epsilon naught A K1 K2. Correct? Now you can cancel out this Q with Q. Okay? What we left with? We left with here is 3 times epsilon naught A by D times K1 K2 upon K2 plus twice K1. Let's substitute. Now what is epsilon naught A by D? Epsilon naught A by D is 9 picofarad, which is here. Okay? So let's put here 9 picofarad. So 3 into 9 picofarad, 10 to the power minus 12 into K1 K2. K1 K2 is what? K1 is 3 and K2 is 6. K1 is 3 and K2 is 6. Whole divided by 6 plus 3 2s is 6. Okay. So we left with here, let's keep this picofarad on the other side. 3 into 9. So 3 into 3, 9, and let's just keep it for the time being. 3 into 6, okay, 12. So that we make it little easy to simplify. And here, now we have 6 2s, and then we left with 3 3s are 9, 9 9s are 81 by 2 picofarad. That you can divide and make it much more simple. So this is our answer to the last question.